Hello friends. Let's talk today about the topic of pointers in C++. Pointers are a tool that can add immense flexibility to your program. They give you the ability to put your fingers directly onto memory locations. Now, for that same reason, they can become a little daunting. Pointers are not complex in and of themselves, but their usage can be a little complex because it's difficult to debug. It's difficult to lay your hands directly on where your data elements are stored. So a thorough understanding of the fundamentals is going to go a long way as we begin to explore this topic. Stick with it, and I think at the end of this video you'll have a pretty good understanding of what a pointer is and what it can do for you. A pointer is very simply a variable that contains a memory address. So rather than having a named memory location that contains some data value, a pointer contains the address of a specific memory location, and that allows us to do a number of different things. So if we look at the example that's in front of you, we have pointer underscore x, and we assign the value 1, 2, 3, 4 to that. What value is stored is the hexadecimal address that you see off to the right that tells us where that memory location is as it was set in memory. There are two operators that we need to introduce right off the bat. The asterisk is known as the dereferencing operator, and the ampersand is the address of operator. And they work in two different things, but they work in concert in order to allow you access to memory. The dereferencing operator is what you will use when you are declaring a pointer variable. So you'll see in the syntax layout we have data type asterisk identifier. Now you'll see in different people's code, if you look closely, you'll see that asterisk slides around, sometimes closer to the data type, sometimes closer to the identifier, sometimes right in the middle. It really makes no difference at all to the compiler. The compiler understands what you're trying to say. My preference is to place the asterisk up against the identifier name. So integer asterisk x creates a pointer variable known as x, and then I can utilize that to contain memory addresses. When you declare a pointer variable, you don't want to leave it uninitialized. If you do, whatever garbage value that it picks up, it will attempt to read that as a memory location. It may be valid, it may be invalid. So we always want to be sure to initialize any pointer variable that we declare. So in this case we've taken integer pointer x, and we are going to give it an initial value of null. If you've not seen null before, we're going to begin using it quite a lot with pointers. And null is an undefined memory location. No, not undefined. It is a non-memory location. Most C++ compilers only recognize null when it is in all caps. It is a constant that is declared as a non-value. Now what this does is, should my program attempt to work with this pointer, it's going to return an address of null, and my program should be able to understand that when it has an address of null, it's an invalid pointer. Now what this pointer is doing, I keep mentioning the integer part of it. When we declare regular variables and we said we wanted integer x, the compiler would go out and allocate a sufficient amount of memory space to contain one integer. however big that is, defined by the compiler / operating system, however many bytes it takes for, or bits, depending on how big it is, to contain that integer value. Now what this is doing is just going just a half step further. It's saying that when we finally allocate x, it is going to be a pointer to a piece of memory real estate sufficiently large to contain an integer. So same idea as integer x, just the pointer is going to contain the memory location of that space. The other operator is the dereferencing operator, and you've already worked with this operator. If you remember when you were doing passing by reference into your functions, you use the ampersand, and now you know what it means. The ampersand operator says, show me the value that's stored at the memory address of a specific variable. So when we go to utilize that, when you were passing those parameters back and forth through the use of the ampersand, what you were doing is, instead of making a copy of the data, copying it into your function, operating on it, and then discarding that operation, and then going back to the calling function, you pass the address of the memory location, or you pass the address of where the data was stored. Your function was able to work directly upon that data, and you didn't need to return it because the data was already stored in the calling function, or even further down the chain, depending on where you started the process. So here you see our code's getting a little bit more complex. I have an integer variable called x, and I have a pointer variable called p. I am going to assign the value 25 to x, and then I'm going to assign the address of variable x to p. So it's passing that value back to my pointer. So when I go and perform my cout operation, what I'm going to get is 25, because it's giving me the operator. I'm sorry, it's giving me the value of that variable. If I want to see the address of that variable as opposed to the value, what I'm going to have is I replace that asterisk with the ampersand here, and now when I see out this value, I'm going to get the hexadecimal address where that value is located, rather than the data value itself. When you use pointers, you gain a new flexibility, and you are able to directly manipulate specific regions of memory depending on how you've declared that. So you can see I've added some new complexity to this. We assign the value of 25 to the variable x. We assign the address of x to p, and then using the dereferencing operator, I'm assigning the value of 50 into p. Now you can probably guess what's going to happen. That's going to overwrite what was originally in x. And so when we process that, the 50 is now in that location because I passed the address, I made my assignment to that new address, and so it overwrote what was originally in there. One of the things that comes with this new flexibility is the requirement to handle garbage collection. New languages, Java, the .NET languages, pretty much everything that utilizes pointers, performs automatic garbage collection. And some new iterations of C++ are performing some manner of garbage collection. That is cleaning up after yourself. And at this point in your programming career, if you're just beginning to explore pointers, we're going to want to do the garbage collection ourselves. We're going to want to make sure that things get cleaned up on our own. Reason being is that we can create something called a dangling pointer, or some people call it a wild pointer. And these can create some very difficult situations to debug. What a wild pointer or a dangling pointer is something that you declared, you utilized, the memory location gets freed, but then you call it later on in the program. It becomes an undefined value. And you see there's a little snippet up there in the upper left-hand corner. We had a pointer called Q. We allocated some memory for it, assigned a value into it, and then cleaned up. We deleted P. If I later tried to call pointer P and assign that 54 into it, what I will get is it may overwrite some existing data, or it may cause the program to crash. So dangling pointers are a bad thing. The only thing that might be worse than a dangling pointer is a memory leak. A memory leak, again, is one of those things that may or may not happen. What a memory leak is that when a program has allocated memory but has failed to release it, to free it up, it begins to eat away at the memory. If you do a little Google search on this, you'll find that some big software packages had known memory leaks in them, and what happened was users would start the program, they would work on a little bit, close it, start the program again, work on a little bit, and by the end of the day their machines were almost ground to a halt because there was a memory leak. Memory was allocated by that piece of software. It was not properly released back to the operating system, and so every time the program was executed, it took a little more, and never told the operating system that it had released that memory. So we assume that any modern operating system releases memory allocated to a program. We assume that, but we don't take it for granted. And so when we begin working with pointers, in addition to looking for those dangling pointers, we're also looking to make sure that whatever memory we have allocated within a program, we also release within a program. Now this is just a broad overview of pointers. This is to give you an idea of what we're going to be working with. In its definition, a pointer is very simple. It is simply a variable that contains the address of a memory location. In its operation, it actually takes a little faith to believe that that is true. So we're going to look at some further code and then look at a program that demonstrates the use of these pointers. Well, if you remember how cool you thought arrays were the first time that you encountered them, began to work with them, and you had that nice data structure that you could put a bunch of data into and really manipulate it quite easily by moving from subscript to subscript. One of the things that began to strike you was that it's very inflexible. It's inflexible because you have to declare the size of a static array at compile time. So that means that before you even distribute your program to your users, you have to have decided how big that array was going to be. Well, one of the things that pointers introduce to us is a replacement for that inflexibility. In other words, we're able to utilize the pointer to dynamically declare data elements or data structures within our program at runtime. And that means that the user is now in control. They can tell us how big the program is going to be. When we use a pointer, and we're going to use the array as an example, what it allows us to do is ask the user how big they'd like an array to be. The user can give us a variable now instead of a constant, and once we have that variable, we can go out, use the pointer functionality to declare an array of variable size and utilize it just as we would use the static array that we already recognize. So you see in the code snippet here, we kind of walk through this process. We allocate an integer pointer because this is going to be an integer array, and we're going to call it list. So that is actually going to be the name by which the array is known. So it recognizes that the amount of space that it's going to have to allocate is going to be variable times the integer size. So we're going to ask the user, tell me how big you'd like this list to be. They give us a number, hopefully greater than 0. We would error check that. And then we go and declare the array. Once we've declared that, we operate on it just like it was a static array. When we begin to work with this stuff, there are two new operators that we need to understand. The new operator and the delete operator. They are both keyword operators. And they are necessary in the process of allocating memory for our dynamic structures. New performs an important task in that it goes out and it actually allocates memory. It goes to the operating system, makes a request, and says, I need X amount of heat memory, grabs it, finds the root memory location and returns that value. So you see we have integer p as a pointer declared. When we use the new operator, we say p equals new, keyword new, integer. So that is the size of the memory space. So it is going to go out and allocate one single integer's worth of memory location. If it is successful at doing that, the new operator will place the address of the allocated space into the pointer p. When I want to assign a value then into that memory location, I use the dereferencing operator and an assignment operator and put my 37 into the memory location known as p. If new fails, if your memory should run out or something of that nature, for whatever reason, if it cannot allocate the space, it will return null into p. And so anytime that we use the new operator, we're also going to expect that we verify the operation, verify that it was a success, and not let the user try to write into a memory location that was not allocated. Delete is the opposite of new. As new allocates memory, delete deallocates memory and returns it to the operating system. So we've added on here, we've done whatever we're going to do with the pointer p. Once we've assigned that value in there, after we have utilized that value and the program is about to exit or at some other location, we would say delete p, and that will go and free that memory location, destroy the pointer, and tell the operating system that that memory is once again free and available for use. So pointers are real simple. We're going to go look at a piece of code now And this code will bring all of these concepts together. We will utilize the dynamic allocation, assign the list to a pointer variable, and then use that pointer variable to manipulate some data. When we're done with it and the user wants to exit the program, we will use delete to deallocate the memory and then exit the program. And I think you're going to find it pretty easy once you get a little bit of practice. Now, the next topic that logically follows on pointers for beginning programmers is the linked list. And because that is such a big topic, I'm going to address that in an entirely separate video. So if you came to this video looking for questions on the linked list, move on, go search for that video, and you should find your answers there. So we're going to look at a real simple example of utilizing the pointers, and we're going to use the dynamic array as our example. Remember, our static array, we have to declare at compile time the size that the data structure is going to take. Now we're going to do what you always wanted to do when you first start working with arrays, and that is we're going to ask the user to give us the size or the number of integers that they want to store in an array, and then we're going to dynamically allocate an array that does so. So we had a little snippet of this in the presentation, but let's have a look at what we've got now. So here we've got the pointer called list, and this pointer is going to form the root of our dynamic array. This is going to be the base memory location from which all of the memory mathematics go on that allow us to move from subscript to subscript. We have an integer variable that the user is going to type in the size for, and then I is just insignificant. It is going to be used for loop purposes. So here I'm going to ask the user for the size. So now remember that if you tried to do this with your static array, you would get a compile time error that said this must be a constant value. In this case, you're going to ask the user for a variable value. They're going to give you a variable value, hopefully greater than 0. There's not a lot of error checking in here. And once we have that value, once they've given us something greater than 0, we come here and we allocate memory for that array. So let's say they give us a sample size of 10. The new operator right here is going to go out and try to allocate contiguous memory that can contain 10 integers. If it is successful in doing so, it will return the memory address of the first integer into list, and then list will use that as our access point to get into the array. Once we have declared the dynamic array, it works exactly the same as the static array. You see right here we set up a for loop that goes through the number of times that the user provided for us and fills the array with those numbers, and then turns around and writes those numbers right back out right here. When we are done utilizing that array, we have to do the garbage collection. We have to go clean up. So we're going to use delete, the open and close square brackets, to tell the program that you're deleting an array. And we're going to go clean up list right after that. If you are deleting something other than an array, you don't need those square brackets. So let's run this. It doesn't really do anything terribly exciting, but let's give it a look. Okay, so the user gives us, the user has the opportunity to say I'd like an array of 10. It fills it up 0 to 9. Now we'll have cleaned that up now. That array doesn't exist anymore. Now we can go as high as, let's go crazy, 2500. Allocates the space, fills it all up, and it's done. And then we can come back and say, well, make that an array of 5, and it does it. So the advantage of the pointer is that because we are working directly in memory now, we are able to create data structures that vary in size throughout the execution of the program. You can see now that you have a ton more flexibility than you had when you had to declare your arrays in a static fashion. So that is just a simple example of utilizing the new operator, the delete operator, the reference or dereferencing operator, all of those kinds of things. Real simple. You just need to do a little practice. Now there is one thing missing from this program, and that is the verification that the pointer, or that the allocation operation was actually successful. If we were going to add that in, we would come right here and say if list equals null, and then we'll just send an error message for now, but this is the can't type and talk at the same time apparently. If this allocation failed, it would return a null into that list pointer, and you need to check for that. Every time you use the new operator, you should follow it up with a verification that the operation was successful. Normally what you would do then is, if list equaled null, you would give the user a message that the memory allocation failed, or you're out of memory, however you want to word it. But then you would also preclude all of the code that follows. So the best way to handle this would be to bracket this, close this off, put an else here, and so if the code was good, then process all of that array handling. So if list equaled null, there was an error and it would skip over all of this. But if it was successful, it would go ahead and process everything. So I don't anticipate that this is going to fail. But let's give it a try. 5, successful, life is good. All right, so there's your introduction to pointers. Good luck, and if you're looking for the linked list information, look for the other video. Have a great day. Bye.